So now let's talk about some organic reaction types. There are quite a few of these, but we're really only going to deal with a few. Addition reactions in general are reactions that tend to saturate unsaturated compounds. They happen when a two-piece molecule, H2, X2, HX, HOH, which would be water, adds across a double or a triple bond, resulting in formation of new single bonds and a more stable, lower energy compound. This is a very common reaction of both alkenes, carbon-carbon double bond compounds, and alkynes, carbon-carbon triple bond compounds. Hydrogenation, addition of H2, hydration, which is addition of the water, an H and an OH to the two carbons of the unsaturated bond, or halogenation, addition of X2. We'll see some examples of those. Two reactions that you actually did in the lab were esterification and amidation, or amidization. Esterification is an example of a condensation reaction, and so is the formation of an amide. Esterification involves the joining of a carboxylic acid with an alcohol to form an ester. Water is the other product. Esterification requires heat and a catalyst and is also easily reversed. Amidation is the joining of a carboxylic acid with an amine to form an amide. Water will be the other product. This often requires heat, or in human beings, it requires specific enzymes that can make this reaction happen. This reaction is much more difficult to reverse. So what will probably happen?
What's going to be our strategy? Well, look for the functional group or groups, and then look at the other reactant. Make sure to remember that reactions happen at the functional group. So change the functional group to form a product, or look at the product where the functional group was. Everything else just comes along for the ride. We're going to take a look at addition reactions.
Bromine, dissolved in carbon tetrachloride, is added to pentane and pentene. The pentane does not react with the bromine, and the solution stays orange. In pentene, bromine adds across the double bond to produce 1,2-dibromopentane, which is colorless.
Three test tubes contain bromine. Cyclohexane is added to the first tube, cyclohexene is added to the second, and benzene to the third. The red color of bromine vapor disappears from the tube containing cyclohexene.
We have an alkene, C double bond C, and we have some hydrogen. The C double bond C is very reactive to addition. It would prefer to be a C single bond C. Adding one H to each C of the C double bond C will make C single bond C. The product would look something like this. Expanded, condensed. This used to be the double bond. This is called hydrogenation. It requires a catalyst, and that catalyst is often platinum. So what will probably happen here? We have the same setup, just a different starting compound. C double bond C, we have some hydrogen. Reactive to addition, put one H on each, and we have single bonds, so our product would look like that. Count it out. This used to have one H and another H. Now it has two H's and two H's if you go around. Another hydrogenation requires a catalyst, platinum. What is this set up to do? Well, your eye should be drawn to the functional group, C double bond C, subject to addition reactions of all kinds. With a little bit of acid and some water, the water acts as HOH, and under the appropriate reaction conditions, it's not solubility that we're dealing with, it's reaction. We get an H going to one C and an OH going to the other. Our product would actually be this: expanded, somewhat condensed. This is called hydration. It does require a catalyst, usually a strong acid. It could also simply be called an addition reaction.
So now what will probably happen here? It looks like we have C double bond C, but wait, that's an aromatic system with alternating single and double bonds all the way around the six-membered ring. It's not reactive to addition. Even though there's a two-piece molecule, Br2, it will not add. This molecule will stay the way it is. There's going to be no reaction under addition conditions.
what will probably happen here? There's that C double bond C again. It's susceptible to addition. It would prefer to be a single bond, but the only way to do that is to add something here and add something here. Well, we have a two-piece molecule. So we're going to get a bromine in each place. There'll still be an H here and an H here, but we've now added a bond to a bromine and added a bond to a bromine. This could be called addition. It could be called bromination because it's bromine that's adding, or it could be called halogenation because bromine's an example of a halogen. This happens readily. What will probably happen here? Well, now we have a C triple bond C. This is very unsaturated. It would prefer to be a C single bond C. Failing that, a C double bond C. And the only way to get there is to add H here and H here. If you do it once, you'll have a double bond. If you do it twice, you'll have a single bond. This will just repeat adding and adding until it reaches an alkane, or you use reaction conditions to stop it. So there would be our product. An H and an H would have left a double bond here, and then another H and another H leaves a single bond here. So condensed all the way down. This is another hydrogenation, and it would require a catalyst.
So what will probably happen here? Again, we have a carbon-carbon triple bond. That is susceptible to addition. It will add two-piece molecules, one to each side, until saturated, except if you run out of ingredients. Notice that there's only one Br2. It's not over the arrow, which would indicate that there are many, 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 and there's no coefficient 2 in front of it. So there's only enough bromine to add 1 to each carbon. That means this will actually end at an alkene, more saturated than it was, but still not completely saturated. We would also see the color of Br2 disappear here.
Here's a specific application of a hydrogenation reaction, and that is this. If you start with a vegetable oil, through hydrogenation you can turn it into a soft spread or a margarine. Continued hydrogenation could turn it into a fat.
So what I'm going to do today is saturate a little bit of olive oil just to show you the process. And since this is not going to be a quantitative analysis, I'm just going to measure stuff out kind of by eye. To the olive oil, I'm going to be adding hexane, and the hexane is going to serve as a solvent. Since we're going to be creating a hydrogenated oil or a solid oil in here, we need to have a solvent to prevent this from basically forming solid chunks and making the reaction slow down. So the hexane just serves as a carrier to keep everything liquid. In order to make this reaction happen at room temperature and low pressures, we're going to use a catalyst. So I have this palladium on carbon, and it says 10%. So 10% of this by weight is palladium metal. We can't just take a chunk of palladium and put it in there because the surface area would be very low and it would be very expensive. So what we do is we coat these tiny bits of carbon. It's basically like carbon dust in there that's been coated with palladium metal, so that when we mix this in, the palladium will be very evenly, intimately mixed with the liquid. Okay, I'll drop in a stir bar, and I'm not going to use the heat on the hot plate. This is just going to be stirring today. And we'll add a cork. And this funny contraption, I didn't have a balloon to put on the top, so I'm just going to use a glove. I'm going to switch on the vacuum pump and then open the blue valve here to pull all the air out of the chamber. Then I'm going to close that valve and open the hydrogen valve so that we fill the thing up with hydrogen and you'll see the glove inflate. And I'm going to do that about 3 or 4 times to try to get all the air out of the flask and fill it completely with hydrogen. Okay, so this last time I filled with hydrogen, and you can see the glove is inflated, so there's a very low amount of pressure of hydrogen gas in there. And I'm just going to leave it stirring unheated for about 1 to 2 hours. As you can see, the palladium has assisted the fatty acids in absorbing the hydrogen gas that we pumped in. And you can even see that the solid form, the hydrogenated, saturated form of the fatty acids are coating the inside of the flask here. So now the job is to filter out the catalyst as well as possible and see what kind of product we have. But now we want to get rid of the hexane, so now all we have to do is boil it away. The oil has a much, much higher boiling point than hexane, so we have a wide window where we could heat it up and just let all the hexane boil away. The temperature is 150 degrees C, so we can be sure that any hexane has been boiled away by now, and the boiling has visibly stopped. So what we're left with is the hydrogenated or partially hydrogenated olive oil, and of course it's liquid now because the temperature is quite high, it's 150 degrees C. So we'll let this cool down to room temperature. So here's our finished product. It's basically a spreadable sort of olive oil. It's quite thick and heavy. It's about the consistency of butter, I'd say, at room temperature. And it smells quite a bit like olive oil. The color is actually from the remaining catalyst carbon that I couldn't filter out. Otherwise, it would basically just be whitish or even slightly yellow from the original olive oil color. So aren't we clever in sort of cheating nature into giving us fattier fats, as it were?
This was done because people in America seem to like their fatty substances semi-solid or all the way solid.
Oil modified by hydrogenation. I had to practice for 3 days just to learn how to spell this word. Now, honestly, isn't that one of the dullest, most unexciting things you've ever seen? Of course, the nice part of it is that you won't see it too often, because the only place you find this combination of $2 words is on the Skippy peanut butter label. Now, translated into English, it means that Skippy is made in a way that's different from any other peanut butter. Now, I don't think you'd be interested in any dry, scientific explanation of that process, but I do think you may be interested in what the end result means to you. For one thing, it means Skippy never has any messy oil separation, never needs stirring. Another thing, it means this is a fresh jar of Skippy. You see, Skippy's one peanut butter where that last little dab at the bottom of the jar is just as fresh and sweet and easy to spread as the first. And every bit of Skippy always tastes exactly like plump, selected, fresh roasted peanuts. This may be a pretty drab phrase, but here's what it means. If you try just one jar of Skippy, I think you'll agree. If you like peanuts, you'll like Skippy.
So times change from that commercial and information updates itself. And for over a decade, there has been concern now about the introduction of trans double bonds during the hydrogenation process. So much concern that they've actually changed the process to avoid introducing these trans double bonds. So let's take a look at that.